So if you know the theory, you'd like to be able to predict what the mass is, be able to predict what the nuclear binding energy is. But the proportion of nuclear binding energy differs depending on the nucleus. This happens to be a very stable nucleus, with a 2, 2, it's a magic number. The binding energy per nucleon is quite high. Not only that, you'd like to be able to predict the spin, does this nucleus act like a little magnet? Helium. Hydrogen does, phosphorus does, but there are a lot of nuclei that don't. Helium doesn't. So, theory's not quite there. Okay, so that's some observations on nuclear stability and a little glimpse, not really even a glimpse, just a mention of shell theory. But with those observations, then you have to come up with some kind of theory that can describe those or explain those observations. All right, in the next section, we're going to look at nuclear fission. And so, nuclear fission can be used to do two things. One, nuclear reactors, the bulk of them rely on nuclear fission, for example, U-235, or nuclear bombs rely on the exact same reaction. It's just controlling the kinetics of this reaction. This reaction can easily go out of control. So if we have U-235, this would be the nucleus of U-235, and we have a neutron come in. Does that neutron have to be accelerating fast? That is, do you have to accelerate that in some kind of particle accelerator, like a linear accelerator or a cyclotron?
Yes.
It turns out no. Room temperature neutrons are fast enough to get to the nucleus. That's a surprise. You don't need to accelerate the neutrons at all. Why is that? Yeah, exactly. They don't have a charge. And so there's nothing stopping the neutron from colliding with the nucleus. Whereas an alpha particle, when Rutherford tried to shoot alpha particles at the gold foil, at the gold atoms, some of the alpha particles bounce right back because of the huge repulsions that are generated. Alpha particles are positive, nucleus is positive, so you get a positive repulsion. It just bounces back, unless you have enough energy to. But the neutron can get easily absorbed in the nucleus. When a neutron gets easily absorbed, then we can form. Look at this is uranium, but uranium's element number 92, so that didn't change. But now we have one extra neutron, so it's now U-236. The problem with neutrons can get absorbed by any atom. So, for example, if you're carbon, your body's made up mostly carbon, and you undergo neutron bombardment, it's going to make a lot of radioactive carbon, carbon-14 perhaps, or whatever. And so neutrons cause non-radioactive atoms to become radioactive themselves because they screw up the balance of neutrons and protons. Well, anyway, a neutron activates this U-235, make U-236. The U-236 then breaks apart a physicals into two smaller particles here. In the process of this, it releases 3 neutrons and some energy. The 3 neutrons that are released can in turn collide with 3 more U-235s and generate 9 neutrons. And those 9 neutrons would generate 27 neutrons, and those 20. And so you set up this thing where quickly this reaction could go out of control. If not. And so basically, to have a chain reaction go off like this and create a nuclear explosion, you have a release a tremendous amount of energy in a short period of time. That would be an explosion. And to have that, you would need what they call a critical mass of U-235, which is like a grapefruit size amount of U-235. And that critical mass can sustain a chain reaction in which this thing goes out of control and releases a huge amount of energy.
How many kilojoules per mole?
How many kilojoules per mole? Huge, huge. Let's see here. Okay, if we have a U-235 in a neutron, then it produces those fragments, fission fragments, and 3 neutrons, and this much energy. The amount of energy is easy to calculate. You just use delta E equals delta mc squared. You figure out the final mass minus the initial mass, and that's your delta mass. That comes out to 3.20 times 10 minus 11 joules per nuclid. If you do it joules or kilojoules per gram, it comes out to 8.2 times 10 to the 7th kilojoules per gram. In other words, that would be 82 million kilojoules per gram of U-235, which is huge, right? Per mole, it's going to be an enormous number because a mole of uranium is 238 grams, so multiply that by 238 to get kilojoules per mole. And so you're looking at what? If you multiply that by 238, you're looking at a billion kilojoules per mole, which is huge. And so, at any rate, this is equivalent to the energy from burning 3 tons of coal. So 1 gram of uranium releases as much energy as 3 tons of coal, which is very, well, coal is much more abundant than uranium.
You know, in that picture where you showed the uranium breaking apart, is that like the nuclear waste at the end of that, where it releases the energy and then? Yeah,
then you have other radioactive products like. And then you have a decay series for U-235. The decay series for U-238 I showed earlier, which is different than the decay series for U-235. But you're going to have a lot of daughter products that are radioactive there. And those daughter products that are radioactive, that's the problem. That's what they call the nuclear waste from the reactors. Because eventually the activity becomes... Anyway, you don't want a nuclear bomb. So if you don't want a nuclear bomb, but you still want a lot of energy, then what you do is you have less than a critical mass of uranium in the fuel. There are fuel rods here, so they put nuclear pellets, in the fuel rods here, and then what they'll do is they can control the speed of the reaction by using control rods. These control rods can which would be the orange things here, can be lifted out of the reactor or back into the reactor. And so the control rods are materials that are good at absorbing neutrons. So if you want to slow the reaction down, you put the control rods in there, they absorb the neutrons and slow it down. If you want to speed up the reaction, you lift the control rods out of there and the neutrons aren't absorbed and they can do their thing. But, we have subcritical mass here, so it shouldn't explode. Shouldn't explode. Well, how's the heat transferred? Well, nuclear power is not the most efficient because the temperature doesn't get terribly high. And so the heat transfers just by heat exchange here. And so there's 3 different water circuits here, and they're closed systems. And so here you have this water circulating, which is going to transfer heat. This is under high pressure, so the water doesn't boil, which is going to transfer the heat to a lower pressure system here, in which the water can boil. The water boils and generates steam, which powers a turbine and generates electricity. The steam is condensed by fresh water. The fresh water would come from a lake or river or ocean here. But this water here in the primary cooling system here is highly radioactive. And so this would be heavily radioactive water.
Wow.
But that's why it's contained in a containment vessel like this. Okay, what can happen though is uranium is a metal, and it doesn't have that high of a melting point. And so if this water, let's say if there's some kind of puncture here, and this is under high pressure, if there's some kind of pressure leak or whatever, then the water can superheat and boil and boil off. And so if this goes dry, then it's like your hot water bath going dry, and the temperature is going to skyrocket. If the temperature skyrockets here, then that has the potential to melt the uranium. And if the uranium melts, then you have what's called a meltdown. And the meltdown, you know, the molten fuel should just sink to the bottom of the containment vessel. You know, and then there's something called the China syndrome. Have you ever heard of that? The China syndrome? The China syndrome is they're thinking that the molten uranium will melt through, eventually melt or eat its way through the containment vessel, and then through the earth, and then end up in China, which is what the China syndrome is about. Right, but worse than that is the worry is it melts and then hits an underwater river, you know, groundwater. If it hits an underwater river, you're going to get a steam explosion. You get a steam explosion, it's going to spew out highly radioactive isotopes into the atmosphere, you know, from the steam explosion. And so this is why, like at Fukushima, they're talking about building an ice wall here to stop the flow of the water underneath the reactor. So one that,
Interesting. That's an interesting way to solve that problem.
but it wasn't successful. Was the problem. So I'm still worried because
Then what happened?
I think it's already eaten through. It's just a
probably-
matter of time,
Yeah.
unless they can come up with something. There are people thinking of things to come up with. Well, nuclear power. This is, you know, unlike burning coal, you don't produce a lot of CO2. CO2's, you know, thought to be responsible for the global warming, CO2 and other gases like methane, or whatever else. But, and so nuclear power, as long as, you know, everything stays contained, is safe. You know? Except there have been accidents. 3 Mile Island, you know, partial meltdown due to loss of coolant.
What is it called?
The coolant's just that water supply. Chernobyl is a different kind of reactor. Chernobyl is a graphite reactor, but this thing got so hot that, you know, graphite doesn't really burn, but this thing incinerated the graphite in the reactor. Graphite's very unreactive. This is old. Our book is old. 2011 is the copyright. France and Japan, 2/3 of electrical energy. Just say France now. 2/3 electrical energy is produced by nuclear power stations. Safety record is particularly high for France. Not so good for Japan.
France. Oh.
These are breeder reactors. Breeder reactors can produce plutonium. Plutonium, you know, you know what the lethal dose of plutonium is?
Very low.
Yeah, it's a microgram. Is the lethal dose of plutonium. And a microgram, a dollar bill weighs like a gram almost. So if you cut the dollar bill into 1,000,000 pieces, and one of those pieces would be a microgram worth of plutonium. So plutonium's always frightening, but you know what plutonium is? You know, plutonium chemically, I've read some studies, plutonium chemically is just a heavy metal. And so some people are cutting plutonium by hand, you know, kind of stuff. It's just a metal. Not particularly toxic as far as metal. But plutonium is an alpha emitter. And so the problem with plutonium is people get little tiny particles of plutonium lodged in their lungs. And it constantly is emitting alpha particles. They can't cough out that part, you know, the particle of plutonium. And so,
Can they detect it, like with an X-ray or something, and know what's in there?
well, it depends on how big it is, but yeah, they should be able to detect it. You know, they could detect very small. The way you would detect it is you just measure the energy of because not only does plutonium emit, does plutonium emit gamma rays? No, maybe not. It might be hard to detect because of it's easy to shield yourself from alpha particles.
Right.
Well, if it's so easy to shield yourself from alpha particles, then why is it so dangerous? It's so dangerous because those alpha particles can cause DNA damage, which can lead to cancer. And your lung tissue doesn't have repair enzymes. Did I talk about repair enzymes? You know, when I was in, this is when I was in biochemistry years and years ago, that they're saying that, and I remember this number, you know, every day the DNA in your skin gets cleaved at least 200 times. You know, the bond gets broken. It's got to be more now because the ozone layer is a lot thinner. You know, back in those days you didn't have to wear so much sunscreen. But the problem with your lung tissue is that it doesn't have those repair enzymes. It's not meant to be exposed to a harsh environment, unlike your skin tissue. So this is one of the reasons. But anyway, breeder reactors can make plutonium. Plutonium can be used as a fuel or as a bomb-making material. Plutonium, it's a half-life of 24,000 years, so it's going to be a long-term problem. One of the proposals that came up was they were going to shoot it off into space, you know. But that nothing became of that.
Ew.
All right, unlike fission reactors, a fusion reactor would be great because a fusion reactor would be like the reaction in the sun where you fuse lighter nuclei to create a heavier nuclei. This is going to be exothermic. There's a tremendous amount of energy that's generated in this process too. And it's not shown here, but it's one of the homework calculations, I think. But the great thing about this is an inert gas and it's non-radioactive. Although we do produce neutrons. Neutrons are not good. But those can be. And so the great thing is get rid of the neutrons and then you're left with an inert product. This isn't going to cause global warming and this isn't going to cause any problems with radioactive waste. And so here. But the problem is, how do you get these two to react? Well, you have to have a linear accelerator or a cyclotron. If you have a linear accelerator or a cyclotron, you just have a molecule or two reacting. It's not enough. You need lots of atoms reacting, not molecules, atoms reacting. In order to get lots of atoms reacting, you need temperatures over 40 million Kelvin to initiate.
So just to increase the RMS fast enough to collide.
Right.
This reaction is not spontaneous.
Yeah.
Unless.
The reason this is, the energy's there, this releases energy, the activation barrier is too big, right? You've got a huge activation barrier. No, we call it spontaneous. You know, if there's a driving force, we call it spontaneous. But whenever we deal with reactions, we have to look both at the thermodynamics. The thermodynamics tells us if it's spontaneous or non-spontaneous. The kinetics will tell us how long it takes. And so the formation of graphite from diamonds should be spontaneous because delta G is negative, but it's never going to happen, you know, because of the activation barrier. So we have a name for that. We call it metastable. There are lots of examples of metastable things where it's spontaneous. It should be spontaneous, but it just doesn't happen because of the activation barrier. Well, we might be able to overcome that. People are trying to overcome that. And lithium is also a dangerous material. You know, lithium is the most powerful reducing agent, has very low oxidation potential. So there's handling problems. But you know, this hydrogen is the most abundant element in the universe. So this might be why they say limitless power once the reaction is self-sustaining. Self-sustaining because, you know, to generate these temperatures will be easy once you get enough reaction going because so much energy will be released in this reaction. You just have to give all that energy to the surroundings, which will be more reaction.
Wow, that looks so good.
At 40 million Kelvin, it would melt anything, right? And so they have to confine it in empty space. Here. because if that came into contact with this, it just vaporized. And so they use electromagnetic fields.
Just holding it in place with magnets. That's awesome.
Well, fusion is very promising. But it's not there yet. And so we have to deal with fission reactors. With fission reactors, we always got to worry about radiation. And so let's take a look at the effects of radiation on matter. We have ionizing radiation. You know, ionizing will just have enough, I guess, power described in terms of the number of ion pairs per centimeter path through a material. Oh, we'll just ignore that. We'll just look at the ionizing ability. And so if we look at that, primary electrons ionized by radioactive particle may have sufficient energy to produce secondary ionization. So we might get secondary ionization. But look at the power. Which one has the most power? Alpha particles. And so alpha particles are one of the most dangerous forms of radiation because of its ionizing ability. In fact, alpha particles would have an extremely high reduction potential, right? They're extremely powerful oxidizing agents. You can ionize. Well, you know, alpha particles can knock off electrons, break bonds, ionize things. So interactions with radiation matter, we don't have to worry too much about it. Just it does cause damage. How do we measure radiation, ionizing radiation? We measure it using a Geiger counter. The problem with the Geiger counter is
Where's the cathode?
You have to be close to whatever you're
It's
measuring.
only an anode.
no, you don't have to get close. There's only an anode?
Yes.
Is that all you see? No, there's a cathode. Do you see the cathode?
Where though? What's that?
The cathode is this. This is just stainless steel handle. The anode is in here. Right?
Like the diagram. Yes.
And so what you have is you have gas in here. And the gas doesn't really conduct electricity unless it gets ionized. And so there's a little mica window in here which can allow radiation in. Gamma radiation, X radiation. Also beta particles. And so let's turn this on.
So it'll sound off on all three? All the particles?
Will it sound off on all three particles?
Like, yeah, like gamma, alpha, and beta, and positron, everything.
No. Alpha particles don't make it in there
Just do
because they're going to be blocked by the mica window. Also, yeah, use the paper shields it. For alpha, you need a special detector to detect alpha. And so this is good at detecting beta and gamma. There's natural radiation, right? We're exposed. So, for example, if you go to Denver, you know, the background radiation is much higher than at sea level. And so you could hear it. Do you hear the little beeps? So it would be the ionizing radiation here.
So radiation is that
Our
iron.
vapors do have radiation. It's so hot.
So you guys wanted to see this, right?
Yeah. Where's uranium?
Yes. Well, anyway, this is uranium ore.
Wow.
Here. You see that? From Arizona or Nevada or someplace. Yeah. This is lead. Here.
Like shooting.
Lead sheeting.
Oh, it's still giving off a bunch.
You hear that?
Yes.
Those are all betas coming in?
Yeah, that's bad.
Yeah.
I don't want to be holding this.
Is that beta particles?
This is gamma radiation.
Oh, that's gamma. Those are the punchers.
It's all right. Yeah, I brought a Geiger counter on a plane.
Feel my nuts on
It was a solid. I mean, at least this I can hear click. So, no. As long as I don't eat this stuff, I'm okay. You know, if you eat this stuff, then you're like the polonium guy or something. You know.
People that fly are more prone to cancer because they're flying in a thinner atmosphere, and so that they're more exposed to the radiation of high altitude.
Yeah.
Uh-oh, I didn't
Yeah,
know
you're going to be
that.
exposed to a lot more radiation at high altitude. But you know, there's a lot of confusion about radiation because you know they're talking about Fukushima. They were talking about, you know, oh, that's equivalent to taking a plane trip to an international plane trip. But you know, there are two types of things. There's one type of thing where you take a plane trip and you get off the plane and it stops, right? You're done with it. There's the other type of thing where you ingest it, and so like strontium gets incorporated into your bone, or there's a plutonium particle lodged in your lung, or you have iodine concentrated in your thyroid. You know, there you can't just open the door, get off the plane, and that's it. That there it stays with you, continuously bombarding you with radiation. So even though the level might be low, it's chronic because it's always with you. You can't escape it. It's like the polonium. You know, that was low-level radiation, but considered low-level radiation, but they couldn't get it out of his system, right? Whereas if the polonium was there on the table and he was exposed to it, then people would say, okay, it's no big deal. You've had your dose of radiation. You should stop. You know, when I used to work with X-rays, did I tell you about this? When I used to work with X-rays, we carried a little radiation badge. And the radiation badge, every month we turned in our radiation badge. And then they say, okay, you didn't have your monthly dose of radiation, or you've exceeded your monthly dose of radiation. Either way, it's too late because you wait a month and they say, oh, you've exceeded your monthly dose. You can't go near radiation for a while, you know. And I was thinking, God, that's ridiculous because if you get exposed to a huge, you want to know, right?
Looks like the bottom of that box might fall out. Be careful. Will your hands show exposure now that you've...
I don't know. I touched it.
Wow.
Oh, maybe I did. Well, I better wash my hands.
You walk the rest of the particles are coming in. You have the lead on you guys.
Well, you know, people mining the stuff were breathing in the dust and whatever else, you know. Yeah, it's not like I'd want to be breathing the stuff in, but if it, you know,
How can your hand stop
if I
it?
pass by it, I'm not going to worry about it. You know.
How can your hand stop it?
It didn't stop it. It was just coincidence that the cosmic. What we're listening to is cosmic radiation.
Huh?
Cosmic radiation. Yeah, that reminds me of another interesting thing about radiation. And
Is it harmful?
at IBM, this was years ago. IBM used to make semiconductor chips, and when they were making semiconductor chips, they'd make it in a clean room because the circuits were getting so small. A tiny speck of dust would cause a failure, right? And so they had the cleanest room, but yet their failure rate was consistent. You know, they couldn't, and they kept getting a cleaner and cleaner and cleaner clean room, and still they had this percentage failure. And so one of the engineers there was listening to a different topic because usually electrical engineers don't care about cosmic radiation. But he went to a talk and the guy was talking about cosmic radiation, and then all of a sudden it clicked. You know, they never shielded their clean room for cosmic radiation. And it turned out that the cosmic radiation was causing defects in the silicon, which was causing the rejection rates. And so after they shielded it, then the defect rate went way down. And so it was pretty interesting. But anyway, if it's space travel, you're going to be exposed to a lot more. Like in the plane, which was just, I forgot, 16,000, 30,000 feet, I had to turn it off. It was going crazy, the Geiger counter. It was kind of frightening, actually, to see it go off, because I'd never seen it go off, you know, that high. Unless I went to like Fukushima or someplace like that, then I'm sure it'd be much more crazier there, because I think... But anyway, it works by ionizing the gas. You ionize the gas, and then you can have an electric current. You know, we get a negative charge build up here, positive here, and then you get a current flow, right, from the, where would we get it from? Well, whatever. To whatever. Yeah. This is like a biochemistry lab here. This is what a biochemistry lab, a lot of them look like.
Today.
Danger.
Yeah, so every time I walk by, it's like this.
Right? They might die.
All right, so we should talk about radiation dosage, you know, and so I carried around this little badge. This badge would tell me how many rads I had, radiation absorbed dose. There was only one type of radiation I was exposed to, so, you know, rad was okay. Rad is, you've been exposed to, 1 rad is 0.001 joules per kilogram of matter. But there are other units for it. And that would be a rem and a curie. I don't know why this went in this order. But a rem would be the most useful to know, because what that is it's the biological equivalent. And so they have a quality factor. The quality factor takes into consideration what type of radiation you've been exposed to. And so there's always the question, you know, what would you rather be exposed to, like 10 joules of red light or 10 joules of gamma radiation? And some people will say 10 joules is 10 joules, you know, but it's not, right? 10 joules of gamma radiation can cause a lot more damage than 10 joules of red light, obviously. And so normally curies is what we think about. This will be like curies here. Curies are how many disintegrations you have per second. And a curie is based on the standard. You know, this amount of radiation we get, you know, per second is from a specific isotope. So you can calibrate your instrument. And it turns out there are 3.7 times 10 to the 10 disintegrations per second, or 3.7 times 10 to the 10 becquerels of radiation. So curies and becquerels, but you don't know what kind of radiation that is. Is that gamma? Is that alpha? Is that beta? And so we have the rad, and the units of the rad are grays here. And a rad is, you know, the joules of energy per kilogram of matter. And so not all X-rays have the same energy, nor do all gamma rays. You know, there's a spectrum of energies for gamma and X-rays and light. But this is what you really want. You want to know your exposure in terms of rem or sieverts. Sieverts, so what you do is you take your rad. Your rad is, let's say you've been exposed to 10 joules of radiation. Then you have to multiply by quality factor. The quality factor for X-rays and gamma rays is 1. So 10 rad is 10 rem. But for beta particles, it's also 1. And so that doesn't do much. For slow neutrons, you know, slow neutrons are room temperature neutrons. It goes 3-fold increase. Your radiation exposure goes up. As neutrons, they meet no resistance going to the nucleus, right? You can also have protons, you know, ejected, certain processes. And fast neutrons are very dangerous, more dangerous than slow neutrons or room temperature neutrons. But look at alpha particles. You know, 10 rad of gamma rays is like 200 of alpha particles. It was 20-fold increase. And so what you should just know is that the rem, you know, this is a biologically adjusted dose here, is what you want to know about radiation exposure. We've got some applications. These applications you don't You don't have to worry about. One application is killing cells using ionizing radiation. Problem is how do you concentrate the radiation? So they have different ways that they're trying to concentrate the radiation so it just kills the cancer cells without killing too many healthy cells. You know?